Today, we're going to talk about the speed of sound in the early universe. Most people know that if you want to talk to your friend, the sound will travel between the two of you via sound waves. What this means is that your vocal cords will drive the air molecules into denser and less dense regions, which your friend's ears will then interpret as sound. But the medium doesn't have to be air. At its most basic level, sound is just traveling density perturbations in a medium. Incidentally, this is why there's no sound in space. There's no particles in a vacuum for your vocal cord to drive, so you can speak all you want, but your friend won't hear anything. There are two ways to calculate the speed of sound in a medium. In the first, you take the square root of the bulk modulus, a measure of the stiffness of the medium, divided by the mass energy density of the medium. This is derived from the second method, whereby the speed of sound is defined as the square root of the derivative of pressure with respect to the mass energy density. But how does this help us if we don't know what the early universe was composed of? Well, we actually do. Because light takes time to travel, looking away from Earth is like looking back in time. We can actually see all the way back to the cosmic microwave background, or CMB, the radiation which permeates the entire universe and which formed the primordial soup which made up the universe some 13.7 billion years ago. From this background radiation, cosmologists have determined that the early universe was composed of a few protons and neutrons, a fair amount of positrons and electrons, some neutrinos, and a lot of photons. But how do we get from particles to the speed of sound? Well, that depends on how much you want to include and how much work you want to put into finding the answer. We will be excluding protons and neutrons because they make up only a few parts per billion of the cosmic microwave background. And we will also ignore neutrinos and dark matter because they don't interact enough to make any appreciable effect on density perturbations. Now, we'll be looking at two ways to calculate the speed of sound in the cosmic microwave background. The first using only photons, and the second using photons plus electrons and positrons, which were radiatively coupled in the early universe. In the first case, we'll look at photons only. Now, we need to find the bulk modulus, defined as shown, for which we need to find the pressure, for which we need to find the internal energy and entropy. The easiest way to find these values is by modeling the photons as a photon gas using quantum statistical mechanics. I'm not going to take you through the derivation, but feel free to pause the video or look up the derivation in any basic statistical mechanics textbook. Essentially, start from the energy of a photon equals the momentum times the speed of light, multiply by the Planck distribution, and integrate. From the energy, we can then get the entropy. To find the pressure, substitute the entropy into the energy equation and then differentiate with respect to volume. This ensures that entropy is being held constant. Differentiate the pressure by volume and then multiply by the negative volume to get the bulk modulus. The answer turns out to be nice and proportional to T to the fourth. Now that we have the bulk modulus, we can calculate the mass energy density of the photon gas. There are two parts of the density, the energy component and the pressure component. We already have the energy and the density of a photon gas from our bulk modulus calculations. This easily leads us to our mass energy density, and from there, it's just simple division to find that the speed of sound in the early universe is the speed of light divided by the square root of 3. That's a great answer, but what if we were being too simple? Well, let's introduce positrons and electrons in the mix. In this case, we'll use our second definition for the speed of sound. Here, there's going to be pressure from the photons. We can neglect pressure from the electrons and positrons, and density contributions that will be made by the photons in addition to the electrons and positrons. To find the mass energy density of the electron-positron mix, we need to model those electrons and positrons as a gas and follow the same quantum statistical mechanics procedure as we did for the photon gas. But instead of using the energy of a photon, we're going to use the energy-momentum relation and the Fermi-Dirac distribution. Once you get to the energy stage, assume that the temperature is very high, as it was in the early universe, to get a numerical result. After you get the mass energy density, it's just a simple matter of remembering the pressure and density of the photon gas from before, multiplying by the derivative delta T over delta T, substituting and solving. Notice that we get to a point where we have the density of matter divided by the density of photons. But the density of photons is much higher in the early universe than the density of electrons and positrons. This becomes 0, and once again we are left with the speed of light divided by the square root of 3. But what does the speed of sound tell us about the early universe? Well, we know how old the universe was at the time of the microwave background radiation was formed. Since the speed of sound measures how fast density perturbations travel, we can use it to calculate the width of the largest coherent section of the cosmic microwave background. This value, which turns out to be 230,000 light years, is called the sound horizon. Since we know what this length is absolutely without reference to Earth, distance, or velocity, we can use it to transform the angular measurements taken by telescopes to absolute measurements and produce maps of the cosmic microwave background, like this one from the WMAP satellite. Cosmologists can then use maps like these to help map the structure of the universe, since differences in the cosmic microwave background led directly to the galaxies we see today. This, in turn, helps map the presence of dark matter in the universe. Thank you so much for watching. If you want to look up more about the early universe, please feel free to consult any of my references listed here. Thanks go to my physics professor, Dr. Kolan, for helping make this video possible. If you want any more information or have questions, feel free to contact me via the comments section below. Thank you for watching, and goodbye.